Welcome to this course on Elements of Mechanical Engineering. My name is D.A. Ramacharyulu and working as an assistant professor in the Department of Mechanical Engineering. In this lecture, we are going to study the working of a Francis turbine. We are in the second module where we are studying different types of steam boilers and hydraulic turbines. First part is completed. In hydraulic turbines, in the previous section we have seen different classification. Apart from the classification, we have seen the working of a Pelton wheel turbine, and also we have seen the efficiency and work done by the Pelton wheel turbine. In this lecture, we are going to see the working of a Francis turbine. So we have seen in the classification that there are two types of turbines. One is impulse turbine and second one is reaction turbine. Impulse turbine is the turbine where there is only kinetic energy present at the inlet of the turbine. Whereas in reaction turbine, we have pressure energy along with kinetic energy when the water is entering into the turbine inlet. Now in this lecture, we are going to see Francis turbine. Now let us try to understand the basic construction of the Francis turbine. So you can see in this picture, Francis turbine is a closed chamber turbine. Here the entire thing is closed. That means the pressure inside the turbine is different from the atmospheric pressure. The water, when it is entering into the turbine, initially the water comes from the dam through a pipe called penstock, and the water, when it is coming from the penstock, it will be coming at a very high velocity and it has very high pressure because we will arrange a nozzle type of pipe to this penstock where the velocity and pressure of the water will increase. Now, when the water at this high pressure and velocity entering into the turbine, it will make the turbine rotate. The turbine will be rotated with the help of the pressure energy. In Pelton wheel turbine, we have only kinetic energy. In this reaction turbine, we have both pressure and kinetic energy. Now, see here, this is the entry of the water. This is the point where the water enter into the turbine and it will make the turbine rotate. Okay. Now, let us see some basic parts. We have a shaft. Shaft is nothing but it is a metallic rod which is attached to the turbine wheel. And we have guide blades. Guide blades are nothing but these are the mechanical structures which are fitted inside the turbine to make the water flow through the turbine. Like it will guide the water to enter into the turbine runner. Runner is nothing but the wheel which is rotating. And we have spiral casing. Spiral casing is nothing but it is a circular tube in which water will rotate before it enter into the turbine runner. And we have runner here. So this runner is nothing but it is a metallic wheel on which we will have the vanes which are attached. So these vanes are the main thing which are responsible for the rotation of the turbine. And then we have draft tube. Now this draft tube is a very interesting part where the shape of the draft tube is designed in such a way that it will remove the water from the turbine. So we have seen that the pressure inside the turbine is more. Okay, this pressure is not equal to the atmospheric pressure. Okay, so because of this low pressure, here the pressure is low when compared to atmospheric pressure. So because the water will easily move from high pressure to low pressure area, here the turbine will have a low pressure. Because of this, the water cannot be removed easily. That is why we will attach a tube called a draft tube, which is of the shape of a decreasing cross-sectional area. Like this, here the cross-sectional area will be small and here the cross-sectional area will be more. This is small d and this is capital D. This is a cylindrical tube. Now, when the water, after touching the turbine vanes, it will enter into the draft tube. Okay, because we have seen the pressure inside the draft tube is very low. So that is why removing the water from this turbine is very hard. That is why we have designed the draft tube in this increasing diameter. And because of this cross-sectional area, what happens is the water present inside the turbine will be easily removed. And also, this draft tube is submerged inside the water. It is always submerged in the water, and it has to be submerged in such a way that the pressure of the water inside the turbine will be equal to the pressure of the water that is in the sump. When it is left above the water, what happens? The water cannot come out easily. Okay, so because here the pressure is very low when compared to atmospheric pressure. That is why this draft tube has to be dipped into the water. It has to be inside the water so that the pressure is maintained constantly. Now, the Francis turbine operates under medium heads and also requires medium quantity of water. So this is the first thing. We have to choose the Francis turbine, or it is also a kind of reaction turbine where the head is medium. Here the head is medium, and it is employed in the medium head power plants. It is used where the head is very medium when compared to the Pelton wheel turbines. The Pelton wheel turbines are the kind of turbines which can be operated with a very high head of water. But this is a medium head type water turbine. Okay, this type of turbine covers a wide range of heads because it is a medium range head type turbine. It will cover only a small part of the heads. Okay, and the head acting on the turbine is partly transformed into kinetic energy, and the rest remains as pressure head. So this is the key thing in this turbine. Here, the energy that is possessed by the water coming from the penstock, it will be converted into two parts. First one is kinetic energy, and second one is potential energy, also known as pressure energy. In this case, we are calling it as pressure energy. So, the head acting on the turbine is partly transformed into kinetic energy. Some part of the energy is transformed into kinetic energy, and the remaining is converted into pressure energy. This is all due to virtue of this position. Okay. So, there is a difference of pressure between the guide vanes and the runner, which is called the reaction pressure, and this reaction pressure is responsible for the motion of the runner. Okay, see here, there is a difference in the pressure of the guide vanes and the runner. So in this picture, we have seen there are two important parts. One is runner. Runner is nothing but it is a metallic disc which will be rotated when water touches the vanes, and also we have a guiding mechanism which are called as guide vanes. Guide vanes. These guide vanes are responsible for making the water to flow in such a direction that it will make the turbine wheel rotate. Now, this guide vanes and runner, the pressure between these two has to be different. There should be a small difference in the pressure between these two. So that is how the runner will rotate. Okay, if the pressure is same, there will be no motion. Here the pressure is different in guide vanes and the runner. So that is why this pressure difference will make the turbine blade rotate. Okay. Now this is the basic introduction of the Francis turbine. Now we'll see what are the major parts of a Francis turbine. The first one is penstock. Penstock is nothing but it is a large diametrical tube from which the water from a dam will flow. Okay, it is a large tube which is attached to the dam or a reservoir where the water will flow. Okay, so this is where the water will be coming at a very high pressure and high velocity. And second device is spiral or scroll casing. So in this picture we can see we have a spiral casing. So this blue color tube is called spiral casing. So actually we are seeing here is a cross-sectional sectional view of this turbine. So this tube, this blue colored tube will be spiraling around the turbine like this. Okay. So it started here and it went all through in this direction, and again it will go into this. So this is sectional image. So we are seeing the internal parts. So This spiral tube is also responsible for making the water to flow in circular motion. Okay, so when the water enters here, it will flow through this spiral casing and it will have a kinetic energy which makes the water flow in circular direction, rotary direction. Now, when the water is circulating in this spiral tube, it will enter into the runner. So, this part is called runner. This is where it will have some vanes. These are vanes. So, when the water touches the vanes, the turbine runner will rotate. Okay, and this is the cross sectional area of this spiral casing will be decreasing. So, here the cross sectional area is more, and when it goes on spiraling around the turbine runner, the cross sectional area will be decreased. And third main part of the Francis turbine is guide vanes or wicket gates. So these vanes direct the water onto the runner at an angle appropriate to the design. So we have guide vanes. Here see this yellow colored part. This yellow colored devices are nothing but the guide vanes. These are responsible for making the water to enter into the runner. So this orange colored part is called runner, yellow colored part is called guide vanes or wicket gates. So when the water that is flowing into the spiral casing like this, the water will go on rotating around the runner. So this water will be directed into the runner through the guide vanes. So this yellow colored part is called guide vane. So the function of this guide vane is it will make the water enter into the turbine in an effective way. Okay, so these are the three main parts, and we have some more parts here. We have governing mechanism. In governing mechanism, it changes the position of the guide blades. It changes the position of the guide blades or vanes to affect a variation in water flow rate when the load conditions on the turbine change. So governing mechanism is a separate device which is attached to the penstock and the spiral casing. This spiral casing will, the governing mechanism will control the flow of water that is entering into the turbine runner. Okay, whenever we want more speed, like if we want more RPM from the turbine, we will make the amount of water to enter into the turbine will be more. Now, if you want to slow down the turbine, we will let small amount of water that is entering into the turbine. Okay, now this entire thing, increasing or decreasing the flow of water into the turbine casing, this will be guided or this will be controlled by the governing mechanism. We will have a governor depending on the speed, depending on the requirement, we will change the speed. And then we have runner and runner blades. So runner, the driving force on the runner is both due to impulse and reaction effects. The number of runner blades usually varies between 16 to 24. So in this picture we can see this orange colored part. This is called runner. So what is the function of this runner? So runner is a rotating device on which we will have a mechanical metal plates attached. These are called vanes. So these small serrations are called vanes, which when water touches these vanes, they will try to move so that the entire runner will rotate. So this movement of the vanes, because they are attached to the runner, the entire runner will rotate. Okay. So runner and runner blades, the effect of force that is acting on the runner and runner blades is due to both impulse and reaction effects. That means there are two types of forces acting on the runner. That is, one is kinetic energy. We have seen in the previous slide. One force is kinetic energy and second one is pressure energy. It is not potential energy. Here it is pressure energy, and it is also called as reaction effect. Okay, because of these two forces acting on the turbine vanes, the runner will rotate. And last part is draft tube. Here we have this draft tube. Okay, when the water After it entering into the runner, it will come out in the perpendicular direction like this. Here, initially, the water will rotate in this direction, in spiral rotation. Okay. And once it entered into the turbine runner through the guiding mechanism, and from there it will come out of the runner in perpendicular direction, that is in the downwards direction. Up till now it has rotated in the spiral casing in horizontal plane. Now it is coming out of the runner in perpendicular direction, that is perpendicular to the rotation of the runner. Now at this point we have to connect a tube called draft tube. The function of this draft tube is to remove the water easily from the runner. Why? Why do we need to remove this water easily? Why it will not come on its own? We have it. The draft tube is attached at the bottom side. That means due to gravity, the water can easily come out. But the pressure inside this runner is very low pressure. The pressure inside the runner is very low when compared to atmospheric pressure. Generally, what happens? Water will flow easily from high pressure to low pressure. But here the pressure inside the runner is low, from where we have to remove the water to a atmospheric pressure which is more. So that is why we have to connect a tube. So this tube will be circular cross section and it will be of increasing diameter. Okay. Now what happens? Due to increasing the cross section area, the water can easily be removed from the turbine. Okay. So these are the main parts of the Francis turbine. Now we'll see what is the basic layout of a Francis turbine power plant. Here we will have a dam or a reservoir. Behind this reservoir we have water. This is all water. So the level of water present in the reservoir is known as head raise, and we will denote this head raise with capital H. And we have some other heads like HG, gross head. So gross head is the head raise and H is the head, that is net head available to the turbine. And we have HF. HF is nothing but head loss due to friction. So these three are the heads which are to be kept in mind while we are calculating the work done or when we are calculating the efficiency of this Francis turbine. Now we'll see, this is a dam, and inside the dam we have a pipe attached. This is the pipe through which water can flow out of the dam without opening the gates. The gates of the turbine, the gates of the reservoir can be opened whenever the water reaches its maximum level. We cannot open the gates when the water is at normal level or when the water is at below the normal level. So the gates can be opened when the water is very high. Now, for the functioning of this turbine, we need water continuously. That is why we will place this penstock at the bottom of the reservoir, where we will get it is not placed at the bottom, it will placed at a little high above the bottom, so that we will not get all the sand and mud particles into the turbine. We have to filter all those particles before entering into the turbine, or the turbine parts will be subjected to corrosion. Now, so this pipe is called penstock, through which water will enter into the turbine. Here the water will come in this direction and it will enter into this turbine. And while entering into the turbine, we have seen the water will rotate in spiral motion when it passes through a spiral casing, and from there it will enter into the guide vanes, and from there it will enter into the runner, and from runner it will come out perpendicularly and it will be collected at the bottom. Here the water will be collected here. The water will come out through the draft tube. And we have a generator attached to this turbine shaft, okay, where we can produce electricity. Now here we have some definitions like H stands for net head. Net head, it is nothing but the head that is available at the turbine, and HG is the gross head. Gross head is nothing but it is the head of the water available in the dam or reservoir. And HF is the head loss due to friction. So this is the head loss due to friction. Why we have to consider this HF? Because when the water is flowing through the pipe, that is penstock, it will have some losses because the internal surface of the penstock and the water will have some friction. Now due to this friction, the pressure or the velocity of the water is lost only up to some little extent, but still it has to be taken into calculations while we are calculating the work done or the calculating efficiency of this turbine. So some amount of head is lost when the water is flowing through the penstock. Now after doing the work, the water is discharged to the tail race through a closed tube, which we have seen already, and it does not allow the water to fall freely to the tail race because we have a very low pressure inside the turbine. That is why we have kept a draft tube of increasing cross-sectional area. Now we'll see some differences between inward and outward flow reaction turbines. Now first of all, we should know what is inward and outward flow. When we are studying Francis turbine, this Francis turbine is a type of reaction turbine. We have seen in reaction turbine, what is the key thing in reaction turbine? We have both kinetic energy and pressure energy. Both kinetic energy and pressure energy are available for the water before it enter into the turbine. Now, there are two types of reaction turbines. One is inward radial flow turbine, outward radial flow turbine. Now, we'll try to understand what are the differences between these two, and also we will try to understand, although the working of these two turbines is same, but the flow of water is different. Okay, both inward flow and outward flow comes under reaction turbines. The working of these two turbines is very similar to the Francis turbine, which is just now we have seen the working, but the only difference is the flow is different in these two. The flow of water. Now we'll try to understand. The first aspect is energy of water. When we compare the energy of water that is entering into the turbine in inward flow turbine, then here water enters at the outer periphery, flows inward towards the center of the turbine and discharges at the outer periphery. So in this, the water enters at the outer periphery. This is the Francis turbine just we have now seen. So the water will enter at the outer periphery of the turbine runner and it flows inwards at the center. Like I will draw a picture. So here I have a runner. This is the top view of the runner. This is the center where we will connect to the shaft. Now the water will enter in this direction. This is outward periphery where it will enter the outward, and from here it will travel inside the center, and from here at the center of the turbine the water will be removed in a perpendicular direction. Okay. Now the water will be coming out of the draft tube at this point. Okay. So this is inward flow turbine. And then second one is water we are seeing in the outward flow. Water enters at the inner periphery, flows outwards and discharges at the outer periphery. Now this is outward flow turbine, which is just opposite to the inward, where the water will enter at the center. Now the water will start entering here in a perpendicular direction and it will rotate in this direction and finally it will come out. Okay. So water will enter at the inner periphery and it will come out of the turbine at the outer periphery. So this is the basic difference between the inward flow and outward flow turbine. In inward, the water will go from outer periphery to center of the runner, where in outward flow turbine, the water will flow from inner periphery to the outside. Okay, so this is the difference. And when we consider the centrifugal head imparted, so here In inward flow, the centrifugal head will be negative. Negative centrifugal head reduces the relative velocity of water at outlet. So the centrifugal head that is imparted in this inward flow turbine is always negative, because the water is flowing from outside to the inside, like from outer periphery to the center of the runner. What happens is the centrifugal head will be always taken as negative. Okay, the head value, H value, it is taken as negative. And in this condition, that is outward flow turbine, it is taken as positive, because it will increase the relative velocity of water at the outlet. Okay, simple. We can simply understand this. Like when we are increasing the distance from the center, suppose I have a metal disc here, it is rotating in clockwise or anti-clockwise direction. When the water that is, if I keep a water droplet at the center, its velocity is very low, because the center of gravity is staying at the center where the water is being placed. Okay. Now I will place a drop of water at the center. Now what happens? It is rotating about this point. The entire wheel is rotating about this point. The water droplet also rotates along with the plate, but it will not have any relative velocity. It is rotating at the same speed as the wheel. Now, when we are moving away from the center, now if I keep this water droplet at this point, that is at the outer periphery, now what happens? The centrifugal force acting on this will be more when compared to the center. Now the centrifugal force, what it will do is, it will make the water droplet to fly off easily, because the centrifugal force acting on this water droplet at point 2 is more when compared to point 1, that is at the center. So this is the difference. In inward flow turbine, the centrifugal head is negative, whereas in outward flow it is positive. And then when we compare the discharge of the water that is coming out of the the outward or inward flow. So in inward flow, the discharge does not increase. The discharge of water that is coming out of the draft tube does not increases. It will come at the same level as the water that is coming out of the penstock. Okay, what amount of water that is coming out of the penstock will directly come out through the draft tube. And then here in outward flow reaction turbine, the discharge always increases, because we will have more velocity, or we will have more centrifugal head that is acting on the water. Okay, and then speed control. In inward flow reaction turbines, the speed control is very easy and effective, because here the net head that is acting on the centrifugal rotation is negative. So because of this negative centrifugal head, the rotation can be easily stopped, or it can be easily controlled. Okay, and whereas coming to outward flow reaction turbine, here the speed control is very hard, because we have more centrifugal force that is acting on the water that is coming out of the turbine. And tendency of the wheel race. Here the tendency of the wheel race, like when the wheel is rotating at high speed, we can control the speed. Like in this reaction turbine, like in inward flow reaction turbine, the centrifugal head is negative. Because of this, there is no tendency for the wheel race. That means the wheel will not rotate, like over rotating of the wheel cannot be seen. Okay. Now in this outward flow reaction turbine, if the turbine speed increases, the wheel tends to race. That means the wheel will experience some wiggling motion. Okay. So it will be subjected to some kind of vibrations, because the centrifugal force acting on the water on the turbine is more when compared to inward flow. Okay. So this is the reason why the outward flow reaction turbines are no longer in use. They were first developed back in the year 1860s, but they were no longer in use, because the wiggling motion of the runner may cause damage or a catastrophic breakage of the metal parts that are attached in the turbine. Okay, we have to control the speed and we have to control the forces that are acting on the runner. So in order to do that, the inward flow reaction turbine is best suited for producing more mechanical energy. And suitability. So these are quite suitable for medium high head and suitable for large output units. Okay, so all the inward flow reaction turbines are suitable for medium high head and suitable for large outputs also. When we want large output of electricity, we have to go for inward flow reaction turbines. And these are suitable for low and medium head, that is medium head turbines. And when we see the applications of this turbine, so these are used for power projects. These are mostly used for power projects where we will use a vertical shaft that is connected to a generator. Generally, they are called as batteries, but they are not batteries, they are generators. Okay, so this generator that is attached to a turbine which is rotating in the vertical direction, and the shaft will be in the vertical direction, the runner will be in the horizontal motion. Okay, when the water that is coming out of the penstock, it will enter into the spiral casing, and this will make the turbine rotate and will have electricity generation. Now, when we come to outward flow reaction turbines, these are practically obsolete, which means these are once developed when we don't have a practical knowledge of the outward flow reaction turbines. So someone like think differently, like one person has invented inward flow reaction turbines. The best example for inward flow is a reaction turbine, where the reaction turbines are working very finely. And some scientist, he thought that in order to increase the efficiency of this inward flow reaction turbine, he tried different methods. Like one of that method is flowing the water outwards, like the working of the outward flow reaction turbine. So in this, he tried to put the water at the center of the runner, where it will enter into the casing, and from there it will come out of the outer periphery of the wheel. So this is not practically possible because the centrifugal force acting on the wheel will be more, and it will make the wheel to rotate in a jiggling motion. Okay, now because of this, the outward flow reaction turbines were once developed or not used in industry anymore. They are practically obsolete. Now we will see the work done and efficiencies of the turbine. So in any turbines, we have to calculate how much amount of work is done by the water on the turbine, because we are sending water which is at high pressure and velocity onto a turbine. Now we have to calculate what is the pressure or what is the work done on the turbine by the water. Okay. Now in order to calculate this, we have to calculate some formulas, like capital H is equal to, which is the net head is equal to gross head minus head loss due to friction. So net head is nothing but it is the head available at the inlet of the turbine, where gross head, that is H suffix G, stands for the total energy available at the exit of the penstock. Okay. Now total energy available at the exit from the draft tube, this is HF. Okay. Now in order to calculate this, we have some formulas, like gross head is nothing but P divided by W plus V square by 2G plus Z. Now we will try to understand all the terms in this. Now P is the pressure of the water that is coming out of the penstock. W is the molecular weight. V is the velocity. G stands for gravity, and Z is the number of vanes. Minus, we have again small p divided by W, which is same. V square is the velocity and G for gravity, plus G, number of vanes. Okay. If the draft tube exit is at tail race level and the datum is also taken at that level, okay, then this Z will be cancelled. H is equal to P by W, V square by 2G plus Z minus V square by 2G. Here the exit of the draft tube is at the level of the water that is present in the tail race. Then we can directly substitute this formula, V square by 2G. Here Vd is the velocity at the exit of the draft tube. And finally, we have this formula. This is for net head. Capital H is equal to P, that is pressure of the water. V is weight of the water that is coming out of the penstock. V is the velocity, and G stands for gravity. And Z is the distance from the datum. Like if we take the water level in the tail race, the difference between the height of water in the tail race and the draft tube exit, this distance is called Z. Okay. Now we will see with this figure, we can actually draw a triangular figure, that is equilateral triangle. Okay. This is also called as velocity triangle. If we draw the velocity triangle of the turbine, of the Francis turbine, this will look like this. So here, observe carefully, this is called outer periphery and this is the inner periphery. So this is where we are considering vanes. So vanes are nothing but they are mechanical elements which are attached to the periphery of the turbine runner. So if we take runner, this is a runner. On this is fitted on a shaft at the center, and on its periphery we have these vanes like this. We will attach some vanes on its surface. Here there will be no attachment. Okay, so this is the outer periphery. Like all the outer edges of the vanes will form a circular shape. So that is drawn here. This line is nothing but the outer periphery. It is an imaginary line where it will join all the outer edges of the vanes. Now see here. Here, this point, if we consider this, particularly the center one, the center vane is considered. See here, this is inlet. Just now we have seen this is the inner end of the vane and this is outer end of the vane. But for water that is entering in a inward radial flow turbine, this point is inlet. This is where water will enter. And this point is where the water will be exited. This is also called as outlet. Okay. Now that is why this is inlet tip for the water. Water will enter here and it will flow or it will travel on this surface and it finally comes out here. Okay. I will draw this again. The water that is coming out from the penstock, it will enter here. It will travel along the surface of this vane and finally it comes out in this direction. Okay. Now we can see the water is traveling along the surface of the vane. That is where it will create some force on the vane and this vane will tend to move. Now when we have number of vanes that are attached to the periphery of the turbine, like 16 to 24 is the minimum number of vanes that can be attached to any kind of a Francis turbine. Now all these vanes will try to move in a particular direction which will rotate the entire runner in clockwise or anti-clockwise direction. Now in this case we are taking the runner movement to be in anti-clockwise direction. Okay. Now see here, when the water is entering at this point, it will travel along the surface in this direction and finally it will come out in this direction. Okay. Now this is the movement of the water when it is flowing along the turbine vane. Well, now we can simply see, we can divide this motion into a velocity triangle. Okay. Now initially the water will be entering in this direction. So I will notify or I will name it as V1. So this is the velocity of water that is entering into the turbine vane at inlet. So at inlet I will represent everything with 1. At outlet I will represent everything with 2. Now here V1 is the velocity of water at inlet. Okay. V1 is the velocity of water at inlet. I will write all those things here. So V1, velocity at inlet, simple velocity at inlet. Now when the water flowing in this direction, it is not perpendicular or it is horizontal. It is inclined at an angle, like it is inclined at an angle of alpha with respect to horizontal. Now if we draw a triangle, we will draw an imaginary triangle here. When we draw this, we will have this triangle like A, B and T. ABD. ABD is the triangle which is formed at the inlet. So when we compare the ABD triangle, it will have an angle alpha, and we have the velocity of water that is entering, that is V1. Okay, V1 and alpha. These are the two values that are available till now. And also this component like BD. Now we can name this as VF1. Okay, so far we have V1, that is velocity of the water that is entering into the turbine, and VF1, this is the velocity of flow. So the water which is touching the turbine vane, it will flow at a particular speed on the turbine vane. Now this speed of the water which is flowing on the turbine surface or the vane surface, that is called VF1. This is called flow velocity. Okay, flow velocity. Now what is this flow velocity? Why do we have to divide the velocity into 2 to 3 parts? Now initially the velocity of the water is considered as V1. This is V1. Now it is divided into first part, that is VF1, which is nothing but the flow velocity which will make the water to flow on the surface of the vane. And another part is there, VR1, and this VR1 is nothing but relative velocity of the water that is entering into the turbine vane. Now this relative velocity is what responsible for movement of the turbine. Okay. Now the VR1 is nothing but the relative velocity, and then we have VW1. VW1 is nothing but whirl velocity. Whirl velocity. This whirl velocity is the key thing along with VR1. VW1 is the key thing which will make the vane move. Okay. Our intention is to flow water on the surface of the vane and to make the vane move from one place to another place. Now, when we compare this triangle, see, this is VW1. This is the component where it is taken as the horizontal side of this triangle. It is VW1, where this VW1 is horizontal and it is trying to move the turbine vane in the horizontal direction. In this direction it will move. So we are representing this with the help of a triangle. Okay. Now see here. This is the horizontal line and this is vertical line and this is triangle. See here, this is alpha, this is V1, this is VF1, flow velocity, and here from here to here, this entire thing is called VW1, whirl velocity. And at the center we have another component, that is VR1. This is relative velocity. Now because of this relative velocity, we can identify the difference of velocity between the water and the turbine vane. Okay. We have discussed already in the previous lectures what is relative velocity by taking the example of two cars which are moving at two different speeds. When we compare the relative velocity, the difference of the speeds of the two cars will be given as the relative velocity. Suppose if a car is moving at 100 kilometers per hour and the second car is moving at 50 kilometers per hour, the relative velocity is equal to the difference of these two speeds, which is 50 kilometers per hour. Similarly, here the water is coming at a speed, that is velocity V1, and again the turbine vane is moving at a particular speed, that is, in this case we will consider this as U1. U1 is the velocity of the moving vane. Water coming with V1, vane is moving with U1. So the relative velocity will be given by the difference of V1 and U1, which is equal to VR1. VR1 is equal to V1 minus U1. Here, every time V1 will be more because it is the velocity of the water that is coming out of the turbine, coming out of the penstock. And U1 will be slow because it is taking the force that is exerted by the water. Now we'll move to the outlet. Here when we see the outlet part, we have the water that is coming out at a velocity v2. Here this is v2. When we divide this, or if we form a triangle here, this part we have separate components here. Here the main component is nothing but v2. Okay, this is v2, and apart from that we will have another component. Now this is vr2. Here the relative velocity is more longer when we compare it to the inlet. Now if we form this triangle, this will give you the actual values of the whirl velocity. From here to here it is whirl velocity. This is vw2, and this is the velocity of the turbine. Okay, now I will draw this triangle again. So now I'm drawing this outlet triangle. Like this is the inlet triangle. The bottom triangle is nothing but the inlet velocity diagram, and now I'm drawing the outlet triangle. That is, the bigger line is nothing but relative velocity vr2, and the smaller line is v2, and we have a straight line, vertical line, and these are attached. Now from here this part is called vw2, and this remaining part is called u2, velocity of the vane at outlet, and this part is called vf2. This is flow velocity at the outlet. So by using these two triangles, here we have two triangles using different terminology, like we have v1 v2, vf1 vf2, that is flow velocity, vr1 vr2 relative velocity, vw1 vw2 whirl velocity. So u1 u2 velocity of the vanes at inlet and outlet. So using all these terminology, and we using some kind of formulas, and also we will use this right angle triangle and their particular properties. So using all this we can calculate the velocity, or we can calculate the work done, we can calculate the efficiency of the hydraulic turbine, etc. We can calculate many things using this. So this entire thing is the numerical calculation part. Okay, we will have to solve so many numerical examples on these turbine efficiencies and work done. Now if we see the work done formula, work done by the water on the turbine is given by, we'll generally take this in every turbine, we will take this in the same manner. Here rho is the density of water, Q is the discharge of water coming out of the turbine, coming out of the penstock, V1 is the whirl velocity, U1 is the velocity of the vane at inlet, VW is the whirl velocity at outlet, U2 is the velocity of the vane at outlet. By simplifying this formula, we will get this. So this is the simplified formula for work done by the water coming out of the penstock on a turbine vane. Now Q stands for discharge, and after that the maximum output under given conditions is obtained when VW2 is equal to 0. So if you want to get maximum work done from this formula, we have to take VW2 as 0. That means the whirl velocity at outlet must be 0. Previously we have seen that whirl velocity is the key thing which will make the turbine move. So VW1 is the whirl velocity at inlet. If this whirl velocity is completely converted into work done, then we will get VW2 is equal to 0. Otherwise, we will have some value for VW2, that is whirl velocity that is coming out of the vane. So if we want to get maximum work, we have to consider that the VW2 is equal to 0, which will make this entire velocity thing, or entire the work done will be like this. This is the formula for maximum work done. Simple. This entire part will goes to 0, and the remaining part will be WQ by gravity multiplied by VW1 whirl velocity and velocity at inlet. So this discharge in this case is radial. For radial discharge, the absolute velocity at exit is radial. So the discharge, in this case, the discharge of water is radial. Okay, for discharge, the water that is coming out of the turbine is radial in this direction. Okay, so that is also we have to consider. And that is all for in this lecture. So far we have studied the working of Francis turbine, and after that we have seen the work done and the working of actual different parts of the turbine, and also we have seen different terminology that is related to the Francis turbine. So thank you very much. We'll meet in the next lecture.
Like, share and subscribe. Hit the bell icon for more updates.